Okay, so we're ready to talk about integration. As my class knows, if you've already watched the Mad Farmer video and done the worksheets that go with that video, you already know a lot about integration. So when we introduce this course, we talk about both derivatives and integration, and we talk about it in terms of position, velocity, and acceleration. So we know that velocity is the slope of position, and we know that acceleration is the slope of velocity. And we have gone from velocity to position in the previous videos and the previous worksheets. So we're just going to revisit that really quickly. Let's take a look here. We have a tractor in the Garden State Parkway with a velocity of 20 miles per hour. This is miles per hour for 3 hours. And we know already that the area under this curve, right? And it's not a curve per se, but in general, the area under the function is how many, in this case, miles you've traveled, right? It's the displacement or the change on the F graph, right? This is F prime, and we're talking about the F graph. So we always use velocity in position, but of course, it's not always going to be that case. So using this velocity graph, we figured out that this is 20 miles per hour, 20 miles per hour times 3 hours. And the hours reduce, and you get 60 miles. Okay? All right, so yeah, it gives you a big head start. So answer these questions, pause the video, answer these questions, and when you're done, we'll continue. And that means you, Kevin. Okay, so you know this. From hour 0 to hour 3, how many miles north is defined as positive, of course, did the tractor travel? We know it's 60 miles. And we're going to hit this topic, or this point I'm about to make, over and over and over again. That's 60 miles north. We don't know where you started unless they told you in the problem. So we don't know what exit we're at. We don't know what mile number we're at, but we do know we've moved 60 miles north from our original position. So that leads us to this question. So after 3 hours, what exit number is the tractor at? And the answer is we don't know, right? So we know it's plus 60. It's north 60. So we're going to say north 60 exits or miles, really, right? We'll call it exits, but exits and miles are the same on this pseudo-fictitious highway. And we don't know where it started. So we're going to come up with a letter that we're going to use in integration all the time. It's called C, right? So C is some starting exit, right? Some starting number, some starting exit. We don't know what it is, okay? And we got to be careful here. C is really not a variable. It's some number. It can be any number, actually. So this velocity graph could be used in a lot of different problems depending on where you started. Okay, let's move ahead. So let's answer these questions. And there's a big difference here. Well, there's a couple differences here with A and B. So let's see what happens with A and B. Okay, so pause the video. Do the problems, see if you can come up with, if you can't answer it, that's okay, but see how much you can answer, and then we'll discuss it. Go ahead. Okay, so again, it's the same problem. What is the area bounded by F prime of t? F prime of t. Sorry for the capitalized here, it should be small, but F prime of t. The x-axis, x equals 0 and x equals 3. So we're bounded. It's just a different way to word it. They often do word a lot of problems like this. We're bounded by these regions. We're bounded by these regions. Okay. What is the area? And of course, the area is 60, and it has units. It's 60 miles, right? Okay, now here's the important point, right? 2 people drove 2 different tractors for 3 hours today in the Garden State Parkway. Alice started at exit 100 and ended at exit 160. So that means, right, Alice traveled or displaced 60 miles, right? 60 miles north. Okay. And then Bob started at exit 0 and ended up at exit 60, right? So Bob went 60 miles north. Same displacement, okay? They both claim this chart, this velocity chart, represents their velocity over 3 hours. Are they wrong or right? And explain. So they're right. They both are right. They both can use the exact same velocity graph because the velocity only talks about displacement. Okay, so to illustrate this point a little more, we're not going to use the exact same function. We're going to use a different one. we're going to take two functions. We're going to call this y1 equals x squared plus 6, okay? And then we're going to take a function y2 equals x squared minus 1, okay? And what I'd like you to do is I'd like you to take the derivative. I'd like you to find y prime, y1 prime, and I'd like you to find y2 prime. Take you 2 seconds. Go ahead, do that. Pause the video and take the derivative of both of these. Okay, so you'll notice you've got 2x, and you'll notice you've got 2x. Okay, so that was taking the derivative, right? That's taking the derivative, right? So going from, let's say, position to velocity, right? Position to velocity, for example. Okay, so the question is, what if you want to go the other way, right? What happens if you want to go the other way? Okay, and if we go the other way, this is what we're going to see. We're not going to see any of the original problem. We're just going to see this problem, and they're both the same. So someone's going to say to you, given this function y prime, find y, right? They're going to say find y. And they're going to say, given this function here, right, which looks like a different function, but it's not, find y2. And of course, you're going to get the same answer. So let's talk about what that notation would look like in calculus, right? In calculus, we use this symbol, right? We're going to say the integration, which really means the area, that's the integration symbol, the area under this curve, okay? And if we were doing 0 to 3, which we're not, by the way, but if we were doing 0 to 3 in the previous problem, we would have done this, in other words, between 0 and 3. That would give us a numerical answer versus what we're going to do, right? We're going to deviate from a definite integral for a second. We're going to do what's called an indefinite integral. So if I put an integration symbol around this side, right, that's going to tell me to find the area under here. Okay, now there's only one weirdness here, which I'm going to kind of introduce here. Normally we would put dy dx. That's the same thing as y prime, okay? But with integration, actually, we do something a little bit different in how we write it. We kind of put a dy here and we put a dx here, okay? And I like to teach this right from the start because it makes life easier down the road a little bit. So we're actually integrating both sides, and this side's with respect to y and this side's with respect to x. I'll talk about that in a second. But basically, you already know the answer because we did the problem, right? If I was to scroll this back up, right, we know the answer. We know the answer came from x squared plus 6, okay? And the way we do this is, I call it the reverse power rule. So it's just undoing a derivative, right? So I'm going to raise the power by 1 here. So I'm going to take my 2x. I'm going to raise the power by 1. So I went from 1 to 2, see? So raise power by 1. And then we're going to divide by that number, by the new power. Why is that? Well, because when you took the derivative, right? When you took derivative, you took this 2. Let's use our magic pen. So you took this 2, you moved it. Oh, I didn't want to do that. Well, there it is anyway. You took that 2, right? That 2. You moved it to the front, and then you dropped the power down by 1. So you did the, in a sense, the reverse of this, right? So what we're going to do is the opposite. We're going to raise the power by 1, see? And then we're going to divide by that number 2. Now don't forget the original 2 is up here. I know I'm in Magic Pen. So what happens, right? What happens? We raise the power by 1. This 2 is still here, of course. And then we divide by 2, and what do you get? You get this, right? You get x squared, which is what we kind of knew was going to happen, except for one small detail, which is we don't know there's a plus 6 here, right? If we go over to the blue and do the same thing, right? So if I integrate both sides, we'll talk about again what this means. I know that's freaking you out a little bit, perhaps. If we integrate both sides, we're going to also get x squared, okay? So, and I didn't do the left side here. The integration of dy is y. And this is also y. Of course, this was y2. I kind of dropped that notation, but certainly we could put y1. and y2. But you see you get the exact same answer, right? You get x squared. You add 1 to the power, divide by the new power. You get the same answer. But they both started, which we didn't know because we had this blinder down, right? They both started with different values here. So what happens is, just like we talked about in the velocity problem a few seconds ago, they're both right, meaning there's an infinite number of answers. It could be plus 6, right? It could be minus 1. It could be plus 0. It could be anything. We don't know. So when you integrate, you actually don't have all the information you originally did. So we put a plus c here. We put a plus c. Okay, and c is really important. C is any real number, right? Any real number. It's not the same thing as a variable because this means any possible number. It actually means a family of solutions because every number is valid here, right? So when you solve this problem, doesn't matter. I'm going to stick to the blue one now. Doesn't matter. But when we solve this problem, when we integrate on what we call an indefinite integral, this is called an indefinite integral, which I just want to intro here. We're not going to spend a ton of time on this yet. We get a plus c. And the reason for that is we're basically saying is the answer to this problem is an infinite number of functions, right? So x squared plus 6 is an answer, x squared minus 1 is an answer, x squared plus 7, x squared is an answer because all of these guys, this is a family, right? And I'm only listing some of the family members here, of course, an infinite family, because all of these are possible answers to the question, what is the integration of 2x, right? Of 2x, the integration of 2x. Okay? And that's what we call an indefinite integral. Now we're going to go back and focus, or really compare the two, but we're going to focus back to what we call a definite integral, which is what we were doing when we did the tractor, right? A definite integral would look different because you'd have numbers here. You'd say from 0 to 3, for example, if I wanted to know only over 3 hours. See, this gives you an actual function, but sometimes I just want to know what's the displacement, right? A number. So let's move ahead and take a look at that. Okay. All right. So here, just like the previous problem we did, it's the exact same problem, okay? We're given a velocity. In other words, we're given the derivative, and we want to go backwards, right? We're given a velocity, and our velocity is 20. It's a horizontal line. It's right here. It's the same exact problem we've been doing when we did the tractor problem, and of course, over the last, and it's from 0 to 3, and over the last few minutes is what I was going to say. Okay? So if we integrate, and again, I'll explain what this dt means in a little bit, but when we integrate with respect to t from 0 to 3, we get the displacement. We get the displacement. Now remember, this is f prime. This is f prime, okay? And the displacement can be written as f of 3 minus f of 0. In other words, what exit were you at 3? So let's say we started at exit 100. I don't know if that was one of the examples, but we'll just say we started at exit 100, okay? Well, if we started at exit 100, okay, and you know what happens, 60 miles later, 3 hours later, 60 miles later, we were at 160 miles, okay? So if you end up at 160 miles and you started at exit 100, that's equal to 60, which is exactly what we knew it would be. Okay, so let's look at the math that we do here, okay? We go from the velocity to the position. So here's the position graph, okay? And if you want to see what I did, I really did the reverse power rule we just talked about, see? That's another way of 20t to the 0, right? Times 2 to the 0. I don't want to confuse you there with the... It's 20 times t to the 0. You don't normally see the t to the 0, but it's there, right? T to the 0 is equal to 1, right? This is just a number 1. Okay. So let's, if we integrate this, and again, with respect to t, what do? We add 1 to the power. Okay, so this becomes 1, and we divide by 1, right? So this becomes 1. So the 20 stays here. The t to the 0 becomes t to the first, and divided by 1, which of course we can ignore. And we get a plus c, okay? So this is the position function, right? Or it's a family of position functions, of course, because many different positions will have the same velocity. And this is the velocity, right? That's what we started with. We integrated the velocity, and we got the position. Now, what are we going to do? Just like I did here, we're going to take the position at 3 and the position at 0, okay? So if we plug in 3 for t, right, that's after 3 hours. So this is the time, right? This is the time. This is time 2, if you want to think of it that way. And this is the function 20t. So that's 60 plus, I don't know, because I don't know what eggs that I started at, right? So it's 60 minus 0, minus 0 plus c. So I get a total of 60. It's the exact same thing we did before. Only here, we don't know that this was, we made this 100 a minute ago, right? See, that was 100, but I don't know what it is. I don't know what it is. Because somebody just asked me to do this problem, right? They didn't tell me what exit number we started at. We made this up temporarily. We made that up temporarily. But it doesn't matter what exit number you start at. You still get a value of 60. Okay, so here it is illustrated. This could have been 100 like we just said a minute ago. Here's C. All we know is that when you have a velocity graph like this, it produces a delta, right? A change, right? A delta F is 60, right? Or, as we said earlier, f of 3 minus f of 0 equals 60, regardless of what exit you started at. Okay, so hopefully that clears up. This is called a definite integral, as we started to talk about earlier. Definite integral. And when we're talking about velocity specifically, which is what we like to anchor ourselves with in our discussions, a definite integral, in the case of velocity, it's displacement, right? It's displacement. It's just a change. It's a change in the two y values, right? In f, it's displacement of f, right? So when you take the definite integral of f prime, you get a displacement of f. Okay, now let's talk about what I was about to talk about earlier. Let's write our function again. Actually, let's write our function without a variable. So we just had 20, okay? We just had 20, okay. So what I want you to do is I want you to take the derivative of 20t and I want you to take the derivative of 20x. So again, we'll do the y1 thing here and the y2 thing here, okay? So take the derivative of both of these, pause the video, take you 2 seconds, and unpause it and tell me what you found out. Okay, so you found out y prime was equal to 20, see? And over here, y prime 2, this is y prime 1, is also equal to 20. Okay, so that's why if somebody comes along and says, what's the integration of 20, see? And you have no other data, right? So if they put a question mark like this, okay? If they have this, if this is dy dx, of course, right? We should be clear about that, right? I mean, it's implied here, but we know that this is dy dx. But this guy over here, right, this guy is actually dy dt. From implicit differentiation, we know this, right? See, there's a t, there's an x. So they're different. But if this is not here, see, it's not carried down, right? If I only write the integration of 20, you have no idea. So if I drop this again, and I show you both of these problems, somebody says, what's the integration of 20? Well, you might do the power rule and say, well, it's 20x, right? You might do the power rule and say it's 20t. You might do the power rule and say it's 20z. So you just don't know, okay? So what we need is we need to know what was this derivative taken with respect to, right? So we know that this, the difference here, let's upload this, make sure I got the right, I do. So the difference here is that this is dt. dt means I'm going to integrate it with respect to t, and I'm going to get back to 20t. Of course, it's going to be 20t plus c, right? We've got to be careful about that. Where this dx tells me I've taken the derivative with respect to x, so I'm going to get back to 20x plus c. Okay, so now you can understand, even though we may have, let's say, dy ds, right? Some implicit differentiation gave us dy ds, let's say it's 10. Okay? And if you were to integrate both sides like this, it is kind of obvious that you're going to get an s out of it. Okay? But instead of this, right? Instead of this, not that that's wrong per se, but instead of this, we write dy equals 10 ds. See, we write it like this. So we bring the ds over. It's not really multiplying both sides by ds. It's more like saying, you know, the teacher to the student is 2 to 1 in age, right? Is 2 to 1 in age. See, 2 to 1 in age. But you could say also that the teacher is twice or 2 times the student in age. See, means the same thing, right? So it's just a different way of writing a ratio. So that's what we're really doing here. We're just saying dy is 10 ds, right? So the change in y is 10 times more than the change in s. So every time s changes by 1, y changes by 10. Okay, and now when we integrate that, we get 10s plus c. And over here, we get y, right? So I raise the power from s to the 0. Remember, this is 10 s to the 0. So that 0 becomes a 1 divided by 1. And that's what we get when we integrate it, 10s plus c. All right, and then one more quick look at this. I think we did all we wanted to do here, but let's take one more quick look at this. What if I had a parabola? So let's just draw a quick parabola here. And we'll take the standard old plain parabola, it doesn't matter. Okay, but I'm only going to look at this first quadrant here. And I want to know how much area is it inside of here. See, I want to know how much area is in here. And of course, this parabola is y equals x squared. And I want to know how much area is under here. Well, what I would do is I would integrate the parabola. And I didn't say where, so let's say from 0 to 3, right? And you know what this point's going to be. This point's going to be 9. Okay, and we'll say this is 0. So if I want to know how much area is under this parabola between 0 and 3, this is how I would do it. And again, this is called a definite integral. Let's just review that again. Definite integral. And as always, we always like to go back to velocity. If this was a velocity graph, I'm not saying it is, but if this was a velocity graph with time, it's not. It's x, right? We're using x here, so I mean, I'm going to erase the t in a second. But if it was a velocity graph, you'd be looking for how much displacement there was. Or again, and that's true here, how much change in the other graph, right? So if this was y prime, it would be the change in y. But it's called y here, so we're not going to really do anything like that. So I just want to find out what that change is. Okay, so all we do is we do the reverse power rule. So this is x to the third. I add 1 to the power. I divide by the new power. Okay? And now that so this is done, right? So I've actually integrated. I've done the reverse power rule, and then I put this little bar here, and this bar just simply means evaluate. Okay, so this bar means evaluate, because if you remember, as we said earlier, when you integrate this, it's the displacement between two values, 3 and 0, on another graph, right? On the graph that gave you this derivative. So that when you took the derivative of this cubic, you got this parabola. So we're going back to this cubic function. We're plugging in 3 and 0, and we're seeing how much delta in that function there was. I don't have a name for that function, but how much that function changed. Okay, so all you do for that is you plug in 3 and you plug in 0 and subtract the 2, right? So this is when x equals 0, and this is when x equals 3. Okay, always the higher to the lower. So if you plug 3 in here, right, if you plug 3 into this equation, of course, not the original, but what you came up with, you get 3 cubed, so you get 27 over 3. And you get 0, right, because you plug in 0 to the numerator, divided by 3 is 0. So you get 27 over 3 is 9, 9 minus 0 is 9, and that's an area, right? This is the area under this curve. That's the green area here. I should have made it green for you, but that's the green area under here is 9 units. Okay, actually 9 units squared, but that's the area, 9 units. All right. All right, I'm gonna put some problems. I'll put some on backpack for my class. I'll put some problems up here to try, and then we'll go over those in class tomorrow.